Swayam Prabha. Digital India. Educated India.
Good afternoon, everybody. We are going to resume our sessions on precision oncology. We've seen all earlier 4 classes, a very thorough in-depth of the basics of cancer biology, and then we have moved on to study on the hallmarks of cancer. In the basics of cancer, we have just got introduced into the proto-oncogenes, we have introduced the suppressor genes, then we went on to study what exactly the real aberrations that happen in a DNA or sequence or in the chromosome for a cancer to occur. In the hallmarks of cancer, we have gone into the full in-depth detail of the different 8 hallmarks and then what exactly how each hallmark will continue to play its role or it's playing its vital role in the process of a cancer occurring or in a tumor progression and invasion. Okay, now slowly, like it has been like, we now thoroughly know what exactly it's like. It's not like a single hallmark and it is not like a chain or a circle of hallmarks event. Even a single hallmark or a different orchestration of different hallmarks is required for a cancer to occur or a genetic. As we basically know, cancer is a result of genetic changes. It is a more of cancer occurrence. Now, slowly we have just really know what exactly the molecular mechanisms leading to the tumorigenesis or oncogenesis. Now, slowly we go into the what is the molecular mechanisms of carcinogenesis. This is absolutely a little bit not very different from the earlier ones, whatever sessions we have gone through, but we will see what exactly the role of a carcinogen or a mutant here. So if you recollect in our first class, what we said is like, we know a very perfect code of a DNA sequence. We know that A to Z is a perfect code or whatever. It should be in a perfect code which has been totally getting passed on from hereditary or from the somatic genes to form a perfect, to maintain the homeostasis of the whole system. Now suppose this code is not read well, or is this code is mutated by means of an ionizing radiation or by means of an X-ray or a chemical. How does this alter the whole cancer? How does it alter the outcome of the process of a cancer? So this is all what we have learned before. So now slowly we will get introduced to another term here is what is a carcinogen. Molecular processes involved in carcinogenesis. This is we will be further saying just so for example, let's start basically what exactly is a basic definition of a carcinogen. It is an agent that is capable through single or multiple exposures of providing an initial insult or an initial damage which promotes the selective growth advantage of altered cells or cells which are aberrant, and this generates this and as a result of which lesions are generated during progression and which could be resulting in malignancy. This is by far a very simple, straightforward definition of what exactly we know what is a carcinogen. What are these carcinogens? Basically, we are hearing about this term so much nowadays, much every time we associate cancer and carcinogens so well together. What exactly, how can you really eliminate, or what do you really, I mean, how do you really, can you by elimination of carcinogen, do you totally completely avoid cancer? Yes. So any agent that significantly increases tumor incidence by any route, not necessarily inhalation, by exposure to skin or by through oral or whatever, that agent can be called a carcinogen. Now let's slowly shift. Let's get back to our history classes. So I would really like to say no more of the molecular or whatever, even though this is a precision oncology, it is supposed to be to we have really in depth dealt about so many of molecular mechanisms, pathways in the earlier 4 sessions. So now what exactly, how do they identify this chemical carcinogens? So what happened, just go back to your Oliver Twist, when he was doing, just go back to that particular novel where he was cleaning the chimney from. Those, because it's a British setup, that whole story or that novel is, what happens is, like, apart from that, there was a lot of incidents of scrotal cancers, especially in men during their childhood days, who had ended up cleaning chimneys. Were like, now based on that, this particular person, who's called the father of carcinogenesis studies, Percival Pott. What he has said that he proposed that the causative agent was chimney soot that remained lodged in the furrowed folds of scrotal skin, and his observation was the first. But then he really correlate between the occupational cancer, that is, what is occupational cancer, one that is caused by a specific agents in the workplace, for example the chimney soot here. Because cancer, it could have was thought to develop in childhood. It was in 1978. After that, a law was enacted. It is, see, just imagine, it's almost 100 years after this observation. That boys under the age of 18, they should not be as working as chimney sweeps. They then slowly they had brought in some mechanical devices to clean. This all happened during the industrial revolution in. They were now able to relate an occupational hazard and a cancer. Just imagine what a tremendous observation it is. That itself had led to know, when you know the cause and effect in a cancer disease. Then the law was not reinforced until 1875. It was almost took 100 years, for from that initial report to make it as a law. Meanwhile, Yamagiwa and Ishikawa, they reported the first successful detection of cancer by the repeated exposure of your rabbit ears to coal tar. So they just expose the rabbit ears to the coal tar, and this coal tar contains polycyclic aromatic hydrocarbons. Then again, some more carcinogens, then cancer. I'm sure if you come to this particular image, you all must be very, 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 very familiar. It's your X-ray discoveries. Whether so now, what happened when Röntgen made it? You all know the whole story. This suddenly in the early 19th century, there was an increase in incidence of skin cancer among people working with X-rays, or maybe some aberrant skin lesions. So that also, okay, and that is the time when the use of X-ray was getting more, especially for dental purposes, and so people were like, then suddenly this is also, then by slowly they have where this X-ray is also a potential hazard. So then what happened, this particular Edward J. Clunet, to test whether X-rays alone can cause cancer in experimental animals. What did they do? He irradiated 4 rats. So repeating the treatment, as soon as the radiation induced alterations had healed, and he did this for a period of over 14 months. Now, so what happens on only 2, and among the 2 animals which survived, so there was invasive cancer developed. Although those induction of cancer which preceded was those reported by Fibigner and by Yamagiwa Clunet, this has been been regarded as an accomplishment, and then it's, even though it's like a verification of your previous clinical observations. So now, just coming back so quickly, we know that, so just a brief history of chemical carcinogenesis. In 1567, Paracelsus suggested there was a wasting disease of miners, which might be attributed to exposure to arsenic sulfide. Then in 1761, John Hill noted that the nasal cancer, it occurred in some people who used snuff excessively, and then in 1859, Buesen described oral cancer in tobacco smokers. This was all the bigger breakthroughs in for the history of chemical carcinogens. As I said before, Percival Pott in 1775, he had correlated the cancer of that with the work in the chimney sweeps, and that is mostly in men who have worked in their earlier childhood days. So Wren has reported an increased instance of bladder cancer in aniline dye workers in Germany. So now there's a major carcinogen is now believed to be 2-naphthylamine. So now if you just see in UK, Germany, now slowly is this epidemiology of cancer. Now is cancer exactly? You relate cancer to your occupation, epidemiology of cancer. So now we will really going through this very fantastic term, cancer epidemic. Maybe once when we talk about our lung cancer in further in detail, now lung cancer is a epidemic in in the current Asia. So we will really talk about it. How can it be? How can so for example, you have your asbestos linings. This is how there is an increase in cancer incidence where in countries where there's more usage of asbestos. So then again, along with the history, as I mentioned, work with radium. The incidence of skin cancer by repeated X-ray burns is reported. Then again, some more group have went to show the report of induction of sarcoma in rats by X-ray radiation. So this also we have discussed for painting the coal tar on the rabbit ears. Then that it was like then further, what exactly we've defined, what exactly are carcinogens. So now we will slowly know what exactly should you have the key carcinogen, what exactly are the characteristics. It should be electrophilic or metabolically activated to electrophiles. It should be genotoxic. We will refer all these terms, we will just get used to it in this whole course of session. It refers to genotoxic means it refers to an agent that induces a DNA damage, but this damage may necessarily or may not be necessarily be processed by the cell into mutation. I'll slowly explain how this whole thing is led through. Now, one of the characteristic of a carcinogen, it should be a genotoxic and it need not necessarily be a genotoxic. That means even if it is not altering the DNA, it can continue to be a carcinogen. So, and this carcinogen should be able to alter DNA repair or cause genomic instability. So, this is very, very important. As you remember, your hallmarks of cancer when we were discussing the different DNA repair mechanisms, and then how this carcinogens should be able to should be able to bypass, or if it's altering the DNA repair mechanism, yes, it falls into the category of the carcinogen. It should be able to induce epigenetic alterations, it should induce oxidative stress, it should induce chronic inflammation. Please recollect all our hallmarks of cancer where we have discussed about how the chronic inflammation and this particular carcinogens cancer is related. It should be immunosuppressive. It should be able to downplay all your host immunoregulatory mechanisms so that it can overtake. And then this one of the key characteristic of a carcinogen should be able to modulate receptor mediated effects. And can these carcinogens really cause immortalization? Yes, some of them. And these characteristics of the carcinogen should be to alter cell proliferation, cell death, or nutrient supply. So, if the agent is found to induce DNA damage, it is called a genotoxin or the genotoxin. And it is to be shown that the agent also induces mutations in mutagenicity assay, which we will see the Ames assay, and it can be defined as mutagen. So, if this carcinogen is able to cause mutations, you can define it as classify it as mutagen. As I said, electrophiles are electron-seeking molecules that commonly form addition products and generally referred to as adducts. So, with cellular macromolecules, these electrophiles usually form adducts with DNA, RNA, lipids and proteins. Some of these carcinogens are direct acting electrophiles, whereas other requires some process transformation by process called as metabolic activation. Please keep in mind, some of these carcinogens could be really in inert stage. Whenever in the chemically they could be inert, they may not be very active. For example, a benzene or anything, it may not be immediately your skin makes a contact with it. It is not like some of them may not be carcinogen, but only when they are metabolized into the body by the action of your cytokines and all that. So, as we will see, they will become active activated. So, the classic examples of chemical agents that to become carcinogenic are your polycyclic aromatic hydrocarbons and benzene. These usually are inert by themselves. So, how do you classify a chemical carcinogens like your genotoxic, non-genotoxic? Simple. And this is a very crucial component to assess here assess the risk assessment for this particular chemicals and drugs whatever we use in the common day-to-day life. However, I mean, it's not like investigating carcinogenic mechanisms. There is, I mean, there's always a scientific challenge, you know. For example, and always this classification is not very every time agreed upon, and in it most and it's based on the carcinogens mode of action exactly. So some people even categorize this chemical carcinogens according to the function and their mechanisms of action, and also according to their environment of DNA as being genotoxic and non-genotoxic, such as your mitogenic and cytogenic. This is the properties for your genotoxic are like they possess the ability to simple damage DNA. They can lead to mutations in critical genes which results in development of cancer, which we have seen all that we have discussed all that how proto-oncogenes get activated to oncogene, and we have seen how the different cell cycle genes are being altered, and we really know how the gene sequence is alteration is leading to the development and progression of cancer. So now, like, you know, so for example, if chemical it undergoes bioactivation to an electrophilic intermediate and eventually producing DNA adducts in target cells. Its reproducibility gives positive results in the series of your in vitro genotoxic tests. And this particular genotoxic, it induces genetic damage of target cells in short-term in vivo assays. This is very, very important for even like for example your UV light and all that, you know, they really induce a lot of genetic damage for the target cells in the this particular in vivo assays. So, genotoxic carcinogens are those chemicals or metabolites, and they are able to induce cancer by the direct interaction or direct alteration of the genetic material of a target cells. And these carcinogens, they exhibit a direct analogy between their substrate and activity, and their mutagenesis in vitro assays are and they need not even I mean they may not even need high doses also, or sometimes even they need high doses also, and may affect various animal species and injure. I mean, this particular genotoxic agents may not be like for example your ETBR, ethidium bromide, which is the regular wrap chemical we use. It will cause a lot of effect in very animal species and injure diverse organs. What are DNA addicts? How do this genotype? How do these genotoxic carcinogens? They cause DNA addicts. These are but nothing but your covalent bonds which are established with macromolecules, and if not, they are not removed by your regular repair mechanisms, and if they are not removed prior to DNA replications, these adapts may they will lead to mutations. They will result in mutations. If these mutations are occurring in your crucial oncogenes like your RAS or whatever your P53s and whatever, you know, or in the tumor suppressor genes, any of that, you know, which and these which we have seen that they control your cell development and your cells control cell proliferation, right? So cancer development will definitely follow. So, adduct repair is usually coordinated by numerous enzymes and is controlled by different genes. It may be done via the excision of those bases or nucleotides by combined repair, mismatch repair and direct damage. This detection of this abduct suggests that chemical carcinogens where they are they are able to, they have been absorbed and they are acting in the DNA level. When you come to this non-genotoxic, you know, they don't damage DNA. They alter the balance between cellular growth and death. And they do not affect DNA directly. and they may not be able to raise adducts and are negative for on your some of your mutagenicity tests, but they are capable of inducing cancer by a secondary mechanism which may not be related to direct DNA damage. So, lots of non-genotoxic chemicals positive in animal studies exhibit no genotoxic effects in this series of test systems. They include specific target lesions characterized by will cause lesions which is by cell proliferation or sustained cellular hyperfunction and in short-term animal models. These non-geotoxic agents, they produced hormonal, metabolic, pathophysiological effects underlying the occurrence of target lesions in a series of mechanistic studies. This actually it's just exactly what I was trying to tell. For example, you have a genotoxic carcinogen. It will have a direct and an indirect effect. So, you have the electrophile molecule, and then once this is going to it will help in the creation of your adducts, the DNA damaged cells. Supposing your DNA repair mechanisms, whatever we discussed in the earlier things, they get alert, you end up with the normal cells. And then suppose the DNA replication and it's like you have something called, I will tell in my further proxy, we have called in the process of carcinogenesis, we have the initiation, promotion and the progression. You have the first step is your DNA damaged where the DNA, this damaged DNA goes through a DNA replication, and then you have what is called initiated cell with a mutant DNA sequence. Hope I am clear. So, and then suppose this DNA damage when again your apoptosis systems come into play, and then that maybe could be that could go through the apoptosis cycle and it could be eliminated. This whole cell per se is eliminated. So, chemical carcinogens may directly or indirectly be converted to electrophilic molecules that interact with your DNA. Depending on the cell injury level, that is your formation of your DNA adducts, different ways of cellular response may occur with low damage levels. So, suppose if it is a very low damage level, yes, the repair systems will come into play, and then cells or maybe the cells can undergo programmed programmed cell death like your apoptosis. However, due to under cellular replicative pressure, if this particular goes through replication, then the damaged DNA will allow your mutation. Thus, initiated cells carry permanent and heritable DNA changes, or they carry the mutated DNA changes that may, which this initiated cell will be a predisposition to cancer development. First example, this is like just refer back of how the initial whole thing goes. First, this slide shows like carcinogenic exposure. After exposure, it gets absorbed, then distributed. Then, as I said, the inactive one will be be activated, and then you have your biotransformation. Either it happens in the liver, kidneys, and all that. After active, and if it's not activated, some of these carcinogens or chemicals which are not activated, they will be excreted out via your regular process, like through the kidneys, livers, and all the lung. Suppose if it gets activated, no. So, you have your genotoxic mechanisms being coming into play, such as your DNA adducts, your chromosome breakage, your fusions, deletions, segregation, non-dissection. Just recollect in the basics of cancer biology, the first class, we have discussed about all this. And then even after activation, even it also has a non-genotoxic mechanism such as your which may not directly affect your gene. So, what will happen here? You will have your inflammation, activating immunosuppressive, then your ROS and RNS. These are very, very vital compounds we will discuss later on, and then you have your receptor activation, and then the epigenetic signaling. All this would lead to altered gene signal transduction, and then which would lead to hypoabnormality, and then genetic instability, and then the loss of proliferation control, and then they are not resistant, they are resistant to apoptosis. So, these are all typical hallmarks of your cancer. So, suppose this is how a typical carcinogen it is the how a carcinogen will totally lead to its effect in progression of the cancer. This figure is a very good example. Some of this for the metabolic, just remember here for this particular activation. So, first after absorption, how does it activation for genotoxic compounds? Some directly act like alkylating agents. They need metabolic activation. So, usually how do they go through? They go through the cytochrome P450 enzyme system such as your PAH, aflatoxin, vinyl chloride, PHIPs, NNKs, and then one more example is like your metabolism of benzene in bone marrow. So, as I said before, products of this metabolism are electrophilic and DNA reactive. So, is a mutation and a carcinogen or can a mutagen? What is a mutation? We know an alteration, exactly, we've seen it before, exactly an agent which can cause a change in a coding sequence, a mutant which can cause. So, that is a carcinogen and a mutagen are the same. How did they first go on to address it? As we know that nuclear genome is a dynamic system. It has got, it is at different levels of biomolecular activities. For example, there's transcription, chromatin accessibility, and then accessibility. So, it is a very heterogeneous level where there is nucleotide context and there is DNA repair mechanisms. So, all this is susceptible to mutagenesis across the genome. There is a very high frequency of chromosomal aberration and which is correlated with the increased risk of malignancy. So, cell transformation by your oncogenic viruses. If you recollect, we were discussing about your HPV 16/18 and their E6/E7, how they are playing a role in the formation of into the progression of your cervical cancer carcinoma in situ or invasive carcinoma. So, these mutations, what happens? Cancer exists on a continuum. There is always continuity. For example, the cells transformation by this oncogenic viruses implies a change in the genetic information. Now, what happens? Mutations arise as a result of repair and replication errors due to endogenous process and environmental factors. These mutations they are the substrate. So, please keep in mind they are the substrate for the mutation. They are a prelude for the neoplasmal clonal expansion of the cancer cells. And they conferred and always these mutations, they have been conferring advantage. They either being it in a proliferative or a survival advantage or DNA mismatch. They usually confer a advantage. So, on the cancer cells and or maybe onto the host cells, and that is why it is naturally selected. So, a malignant phenotype is inherited in the cell line. Please remember again back to our first Darwin's theory, whatever we were discussing. In the cell line, for example, a cancer cell line has a malignant phenotype. If you see here, like you have the first right from the 0 year, maybe in the between this year, over a span of 0 to 20 years. There could be an initial DNA damage and then a mutation. Then you see still it is like this particular thing is able to grow. This is getting into a small self-sufficient growth cells. There is increase in number. And over the year, these cells, they are getting resistance to apoptosis. And then further, they'll slowly go on invasive. So, in this process, again, as you remember, there will be increase in tumor mass. And as the increase in tumor mass, you will have your angiogenesis. And then once it increases, they will metastasize. This is how how you link your mutation and the carcinogenesis. Genotoxicity to pre-neoplastic biology to oncology. So, Bovary was the first to suggest that chromosomal changes lead to cancer, and in 1916, Thayer introduced the term somatic mutations. Most chemical carcinogens are mutants. But it's a very good analog here. But not all mutagenesis may be carcinogens. There is a it may and most carcinogens and mutagens are strongly electrophoric. Electrophilic reactants. Ionizing or UV radiations and most chemical, they cause lesions in DNA and defects, and these particular defects are associated with high risk of cancer. Very one important term here again which we will be talking here is epigenetic mechanisms involved in chemical carcinogenesis. So here you have a chemical which is it goes through metabolism and it goes through reactive intermediate, and then a DNA abduct is there, and then a DNA repair mechanism, it works functionally. Absolutely nothing to worry, everything it's just a normal, there's nothing big. Coming here, you have a chemical metabolism, then you have the reactive intermediate, the DNA abduct, and here no DNA repair. When your DNA repair mechanism is not there, you have a mutation in proto-oncogene or in a tumor suppressor gene, or maybe here also it could even happen through via your inherited mutations. So now coming to the endogenous metabolism, where the reactive intermediates such as your reactive oxygen species ROS, and then you have the DNA adduct and then the damage, and but still if there is no DNA repair mechanism here with the ROS or whatever, still the mutation progresses, and after that there is an increase in expression of your oncogene proteins, and there is decrease in expression of tumor suppressor, and then your normal cellular signaling, which is influenced by endogenous and exogenous variables. As it goes through progress, what will happen? You have increase in cell proliferation, decrease in apoptosis, decrease in differentiation, then we all these major hallmarks which lead to the progression of cancer we will see. There is malignant conversion, and then there is carcinoma cells. This is how, first example, like epigenetic, it refers to all your stable changes in your DNA on gene expression and chromatic organization. So for example, this genetic changes, maybe they not be necessarily with DNA sequence itself, and they can be mitotically inherited over cell divisions. So epigenetic phenomena including your genomic imprinting, chromosome inactivation, your global reconfiguration of the DNA methylome, and changes to chromatin, all this like your histone modification pattern occur during development and chronic and contribute to the lineage specific epigenome modification patterns, and this is maintained, all this particular in a normal cell, it's maintained over the lifetime of an organism. So but when you have the carcinogenic, all this could be altered, like carcinogenic such as your chemical, your physical, biological agents, they deregulate your common epigenetic mechanism. Please make a note of this very important term. So then as I said, so chemicals can be metabolized. Usually you have the reactive intermediates that form an abduct with your DNA. So sometimes if this abduct is not repaired, as I said, it goes through the mutations. So combine these two mechanisms, here can lead to increased expression of an oncogene or a decreased expression of a tumor express here. These particular two mechanisms. This and further there is a normal cellular signaling. So here that can be influenced by the endogenous or exogenous. So you have your endogenous and your exogenous variables that collectively alter major pathways that regulate all this particular process, and ultimately leading to cancer. This is your outline of, so it's similar to whatever we were talking of it before. For example, here your endogenous process like your ROS, your lipid peroxidation, your amino acid metabolism, and then your exposure to to this particular will cause the DNA, for example DNA damage, endogenous genotoxic compounds, And whereas exposure to your somatic compounds, like example like your food, your consumer products in places in your workplace, like maybe some other, for example, you're exposed to your strong chemical in your workplace or anything. It's not like just not to be alarmed or anything, sometimes in the cellular uptake and metabolism process, it could be inactivated by a reaction with non-DNA targets. But sometimes, after get, if they cause the DNA damage, so there is an increase in risk of cancer. That and then again, after the DNA damage, again, if your DNA repair mechanisms and your cell cycle checkpoint activation, recollect all your cell cyclin, CDK inhibitors, all that which we were discussing. So if these cell cycle checkpoints are all activated, then there is apoptosis, autophagy, and senescence. So then at the same time, if your DNA damage and if there is a damage is tolerated, example like your transcription synthesis and all that, then there will be inheritance of the mutated cells. So here you have the initiation, and then you're having your promotion here. So here again there is once at this particular point also, you have again promotion, you have the expansion. The mutated initial cells will be expanding, it will be invading, it will have an autonomous proliferation mechanism, and again by the sense of your repair mechanisms, it could be eliminated by autophagy or by senescence the mechanism, or if it's not eliminated, it will lead to malignant cancer cells. So one very important essay which we will be talking about now is your AIMS essay. So first, this is for evaluation of your carcinogenicity. For example, you come up with new chemical compounds and you just or you would say it's an antibacterial or an antibiotic. First thing you have to evaluate, does it cause any harm to your normal cells, or does it have the potential to progress to cause cancer, or the carcinogenicity capacity has to be assessed. So this AIMS test, it has been named after its developer Bruce Ames at the University of California and Berkeley. This test uses bacteria, which is a sensitive biological indicator of whether or not can a substance cause a change in DNA. So he started with a specific bacterial strain like your Salmonella, which doesn't it which has a mutation in its gene to synthesize the amino acid histidine. Because of this defect in this particular gene, the bacteria can grow only on media which contains either histidine or some substituents. Or when he exposed this particular agent or this particular bacteria, what he first did is he took a filter paper, then took the blotted the carcinogen onto this particular filter paper, and then he exposed this bacteria to the filter paper containing the mutagen, so that which can cause the change in your DNA sequence. Then what happened? Then many of the bacteria ended up with new mutation in the gene required for making histidine. What happened? The number of colonies were bacteria which cannot grow without histidine started in the absence of in the which can it started growing. If we expose this to some which is if we had exposed this bacteria to a disc which contains which is not a mutagens, for example a non carcinogenic one, there were no changes in the histidine production of gene and the bacteria did not grow. So there were less number of colonies. This AIMS test, which uses Salmonella typhimurium, is which is a reverse mutation assay. Actually, it is a short term test for identification of carcinogens that cause mutagenesis in bacteria as an end point. So this is it includes mammalian metabolism to activate it needs to activate to pro-mutagenesis. There sometimes not very complete correlation has been observed, found between carcinogenicity in animals and mutagenesis using the AIMS test. So here to detect this, basically histidine requiring bacterial strain. So that produces a histidine independent strain by virtue of the effect of your carcinogen on the DNA sequence. This is used in many of all your toxicology labs and almost all new pharmaceutical substances and chemicals that are going to be in use for your clinical studies or for clinical trials. They have to be tested by this particular assay. Example here, the lab rat liver is homogenized. You have the test compound. When you mix the test compound with your lysate here, the metabolic activation of the test compounds by the rat liver enzyme comes, and this metabolic activity activated compound, when it's added to your salmonella bacteria, which is unable to grow in the absence of histidine in culture medium, it will grow. Whereas sometimes that have undergone, and then sometimes without, in the absence of a mutation, when there is no mutation, or if your compound is not carcinogenic or mutagenesis, you will not have much number of colonies. This is a very important test in your drug discovery toxicology studies. So, genetic toxicity and carcinogenetic. Here, the standard genetic toxicity testing, as we have seen, it allows for our relative simple and accurate detection of DNA damage which is caused by treatment with testing agents. But for carcinogenicity, you need to have evaluate the potential of this particular carcinogen or this particular chemical to induce tumor in animal models. So usually the genetic toxicity testing batteries, what do they consist of? Usually a bacterial gene mutation assay, as we have discussed before, and then in vitro mammalian mutation or a chromosome damage assay, and then an in vivo chromosome damage assay. This test battery is simple, it is accurate and economical, and its hazard identification on exposure to set of chemicals which have the potential to cause DNA damage, and or at the gene and chromosome level we can see. Whereas the potential of this particular chemicals to induce carcinogenicity in animals, it is slightly a bit a cumbersome effort, where it requires a 2-year bioassay in rats and mice, and then it requires 2-year exposure and 3 concentrations of your test reagent, and then you need to have your controls. So some of the transgenic have been that cause susceptible transgenic mice models such as P53, HRAS, have been evaluated and considered as your alternative. So you have your transgenic genes with or without this particular genes, mice models such as your P53 HRAS, and you consider it, test this particular carcinogen, and you look for the outcome of this particular disease. This potential of these chemicals to induce tumors, such as that is your carcinogenicity in animals, and to extrapolate, can you extrapolate whatever you do with animals? Yes, can you extrapolate to humans? This particular if it's carcinogenic in say mouse model, debatable, but still it is usually 2 years, more than 3 years of time. This mechanics, because of this mechanistic association of DNA damage and cancer and the practical implications of this particular carcinogenic assays, this particular genetic toxicity assays, or they are very genotoxicity assays they are very vital. You will have the non-genotoxic mechanisms like your proliferation, all that also, like your hormone changes, nuclear hormone receptor activation, all that which we have learned earlier, they can cause it will lead to a multi-stage process. So as I mentioned before, there are many approaches which are for assessing mutational signatures. This is we will be reading a lot about it in this particular ongoing classes actually. So mutational spectra, for example, your polynucleotide mutational sequences. This is your sequences. They provide a lot of insight into the mutational process. So, for example, your exome or your whole genome sequencing of this particular tumor population reflects the traumatic processes operative in the founding cell of the most recent clonal sweep. For a, see, please remember, keep in mind, as we have been always telling, it may not be necessarily, suppose you take melanoma, or it may not be necessary a complete homogeneous tumor population. It could be heterogeneous. So, it could be even a heterogeneous mixture of different cells. So, what happens, so from this, whatever they can take, their single cells can be cloned from the cultured population, and they can be exposed to the mutations, and then they can assess the mutational signatures of this particular expanded cells. The clonal variants of those present in individuals that were not present in their parents. This is again what this particular mutational processes. Suppose you have the clonal variants only in the children and it's not present only in their parents. This indicates the state of mutational process during gametogenesis or early embryogenesis. So, you can correlate. Then sequencing of your cloned cells or molecules from certain selection based mutagenesis. After you say, for example, your transgenic mice or whatever, and then you expose them to your mutations, and then you take the tumor lesions, and then you go for sequencing. They can maybe it is now possible with this NGS, you can obtain mutational spectra from directly sequencing of DNA from or anything from any tissue or any site, whatever. Now, what is carcinogenesis? It is a multi-stage process. Simple thing, it has 3 steps: initiation, promotion, progression. So, carcinogenesis goes through 3 steps, like your initiation, promotion, and progression. So, in the initiation stage, we have the genotoxic chemicals, radiation, UV, viruses, where there is an initiated, as I showed you in the first slide, there is an initiated cells. And with this initiation, there is clonal expansion, and then where all your growth factors, everything will be, will be for very good players to increase your growth of the cells. Then you will have the, still it's in the confined, where it is still in the promotion stage, you have the pre-neoplastic lesions. Here you have your non-genotoxic chemicals in play, and then you have the progression, where your primary malignance. So, very nicely you can see how this particular malignant tumor will form into a secondary tumors by the genetic, there is genetic instability, then there is suppressor gene loss, and there is lot of gene amplification. This is a 2-stage model of skin carcinogenesis in mice. During the initial topical application of your subcarcinogenic dosage of your mutagenic agent, which induces mutations in the target genes in keratinocytes stem cells. So, what happens here? For 2 weeks, there is metabolic activation of procarcinogens and covalent binding to DNA, and then DNA repair or cell replication and fixation of mutation, it will happen. So, in the initial stages, there is a chance for it could be slightly reversible. So, mutation induction in critical target genes happens. Example, it's your HRAS of stem cells in your bulge region of hair follicle or basal compartment of interfollicular epidermis. Here, so it could happen, the mutations. Then over the progression, like, so first 2 weeks, then from between your 10 and 40 weeks, where so then it, after the end of 2 weeks, it will commence your continual delivery of your promoting. You will continue to inject the same carcinogen, and then over that you have your increased DNA synthesis, then you have altered gene expression or enzyme activities, and then you have this particular initial cell, whatever initiating stem cell population, there is always complete expansion here. And then further on, you have more and more cells are getting proliferated, and then there have to be maintained of this chronic cell proliferation, and there is outgrowth of clonal outgrowths. There is development of clonal outgrowths, and then you have your diploid lesions. And further on, you have the, as they progress, how does it happen here? See, between the 10 to 50 weeks, what happens? See, first thing keep in mind here, it is your sub carcinogenic dosage of your, see, suppose you give it a carcinogen dose, you will not be able to really observe the whole effects of all this. What you do is, it's just a win-win situation. You don't want your mice to die at the same time. You want to really observe your effect of this particular mutagen or your carcinogen on this particular mice. So after this 20, 30, slowly there is initiation phase, then there's your promotion, and then there is your progression. What happens in progression phase? Here you have additional genetic events which occur, strictly like your aneuploidy, then there is dysplasia, and then this conversion of this papilloma to a squamous cell typical carcinoma happens, and then there is invasion and metastasis. So here also you can slowly see how the normal cells, this is the this is an histo figure. This is a normal cell, and then you have your hypoplastic epidermis, then there is this papilloma, and then your squamous cell. This is just a two-stage model of your skin carcinogenesis in mice, which is very well depicted here by giving a sublethal dose of your carcinogen. And then here also again, the three stages, of carcinogens, like your initiation, promotion, progression, we can be studied here. So here, as I said before, it is a bit reversible, like normal cell to initiate itself. Yes, there is a chance of reversible. Yes, your repair mechanisms waken up, and then there is a chance. And then slowly from initiated cells, there is promotion, where you have your focal lesions like a papilloma. And then here also sometimes apoptosis, all this can go away. And proliferation, then it is when this progression. So please keep in mind your multi-hit model here: initiation, promotion, progression. This is for the multi-step hepatocarcinogenesis. This is how it looks. You have your initiation, then your promotion, progression, and then the carcinoma. This is the typical liver focus of altered hepatocytes. Here you can see, and then adenoma, hepatocellular adenoma, and then hepatocellular carcinoma. This genotoxic carcinogen produces initiated cells first. Initially, one cell, that's enough, with a mutant genotype. And during promotion, these cells can be, they will be stimulated. These cells by their own paracrine, exocrine factors, or what we have discussed before, they are stimulated to proliferate by tumor proliferating carcinogens to form clusters of initiated cells. The formed lesions are predisposed to progress into a cancer. That's a predisposition. But further on, more exposure to this particular genotoxic and tumor promoting substance, more and more as they are getting, there is acceleration progression by increasing genomic instability and cell proliferation rate. Chemical or physical agents that can serve as initiating or promoting agents, and their primary for molecular targets here. So you have your benzol, you have your the DMBA, then you have your cisplatinum, then which they affect, most of them they are HRAS, and then you have your promoting, that is your TPA, your benzoyl peroxide, then your UV, and then your healing, which here the initial molecular target, or here the event associated it here is your protein kinase C, and or your generates oxidative stress. We will now move on to a very important term or very important events which happen during the molecular mechanisms of carcinogenesis, that is your generation of your reactive oxygen species, that is your ROS. ROS are like when there is an imbalance between the formation of reactive oxygen and or nitrogen species, and then they're detoxified. So once this ROS are generated, they have to be they are detoxified commonly, and this is referred to as, if there is an imbalance, it's referred to as oxidative stress. So ROS are usually highly reactive intermediates of molecular oxygen. They are produced by an product of an endogenous metabolism. Metabolism of any foreign substances also produces ROS, and these ROS are usually here are most potentially genotoxic. So many of these human and animal carcinogens, whatever we have seen the list, they are capable of influencing redox process, and they are able to cause redox imbalance. They usually this ROS they arise from inflammation, and they contribute to genomic instability along with other free radical species. So oxidative damage is considered to be the major factor in the generation of mutations in DNA, and more than 100 different, more than 100 different DNA oxidative DNA attacks have been identified. There is this oxidative damage is been reported in more than 200 clinical disorders, including your inflammatory bowel syndrome and of course cancer as well. So here, just pay attention here in normal cells. This gives like they have a fundamental role. I want to show how this, ROS have a fundamental role in cancer cells. In normal cells, green cells, cells which are under normal homeostatic balance here. Redox is also there is a basal level of ROS and there is a basal level of your antioxidants. So, but everything is normal. But suppose there is increase in like your cancers, like whatever your exposure to carcinogens or maybe smoking, which we often associate with a high risk of cancer, and then obesity, then UV light exposure. What happens is like there is increase in ROS levels, which induces DNA damage, which includes genetic instability, and then there is precancerous lesions, and then you have your ROS elevations and your antioxidants decrease. Here your antioxidant activity, the DNA repair mechanisms, everything they will be in decrease. See here you see the slightly the red cells. The T suppressor proteins such as your P53, they are all being activated in response to cancer inducing stimuli, repairing DNA mutations, and those inducing the transcription of the active oncogenic genes. Now further on what happens, how do they do that? These pathways are often whenever there is your repair mechanisms are insufficient, ROS and your antioxidant levels rise, creating a new and altered redox balance, thereby favoring the activation of your intracellular oncogenic signaling pathways and maintaining the functionality of cellular components in cancer cells. Like this, the red cells here. These pathways are, are often related to increased cell proliferation and survival, and cell metastasis, and cytokine secretion and drug resistance. So, high levels of ROS, there is increase in antioxidants, and there is altered redox in equilibrium, as you can see, and which will lead to increased proliferation, cell survival. And so finally, an excess increase in ROS due to overwhelmed antioxidant system provokes a loss in redox balance, or there is a complete redox imbalance, thereby inducing your apoptosis and necrosis here. Can you see this? So these pathways are often related to increased cell proliferation, survival, metastasis, cytokine secretion, and drug resistance. There is an at this point, activation of your P53, activation of your P53 due to severe cellular damage can induce cell cycle arrest, senescence, and cell death. Here you can see the gray cells, probably which can suggest a differential response to ROS response depending on the oncogenic background and on the P53 status of the tumor. So they have here, I want to ascertain that, or ROS, they have a very prime role in cancer. Here you can see if your ROS levels are low, basal ROS levels are, it's in the normal scenario, whereas your tumor promoting ROS levels are again increased. Then the tumor suppressor, again the high levels of ROS, the redox equilibrium is lost, and thereby activation of P53 due to cellular can induce cell cycle arrest. Quickly we will discuss about the signaling pathways which are mediated by the ROS here. They have a fundamental role in cancer. They can inactivate what we call it as a red burst or activate. Here you see the green burst. ROS activates your NF-kappa B pathway. NF-kappa B pathway, thereby by favoring the dimerization of and inducing phosphorylation of the NF-kappa B inhibitors, which are later degraded by your proteasome and induce phosphorylation of the P50, P65 dimers. These are all your different pathways, which are totally altered. One more, RAS also favors the oxidation of your protyl hydroxylases, PDHs, prolyl hydro, which are the key to the union of the VHL protein with your HIF 1 alpha hypoxia inducing factor, which you recollect, inducing its ubiquitination and degradation in the proteasome So again you have your the D here, please see the D, I am zooming it for you. Here TRX is oxidized in the presence of H2O2 and separates from inducing phosphorylation of your MMK, which in turn phosphorylates JNK or P38, facilitating transcription of genes related to cell proliferation and differentiation, apoptosis, inflammation, all this we have seen, right? And stress response. Finally, you have your P10 phosphate is oxidized and inactivated by your ROS, which promotes the activation of your P13K AKT pathway related to cell survival and proliferation signaling, as well as your protein biosynthesis. Here if you see, here you can clearly see how well all these particular signaling pathways are well influenced by the presence of H2O2 or your ROS in your particular, and they all play a very key role in the outcome of your cancer. Just a quick note for the different chemical carcinogens, like you have your polycyclic compound aromatic hydrocarbons like your benzopyrene, and then which forms what is it, the role it has, it forms adducts with your purine bases of DNA, mainly resulting in invasiveness. So it affects your these are the different, this slide gives the chemical list of your different chemical dyes and the mechanism of their actions, and then where exactly do they affect. So usually ROS is very important in your for the outcome of your cancer. Usually it is always said that increase in consumption of your fruit or your vegetables, which they have a lot of high quantity of your anti-cancer, has been associated to increase in cancer scenario. For example, your dietary polyphenols, your xanthones, glucosides, and your sulforaphane have been shown to have antioxidant effects on the or they are able to modulate your antioxidant effects. It is still remains to be established whether their cancer preventive effects are mostly mediated by their antioxidant properties or by the combination of the cancer suppressive effects. This is all in the new process of development and still in the process of conceptualization. Finally, exposure to UV light, we all are aware that it is going to cause cancer, right? Skin cancer. So, exposure of cells to UV radiation is directly known to induce DNA oxidation by the formation of 1O2 and 8-hydroxy deoxyguanosine. It is called A2HDG, which is the main product of your guanine oxidation, and it by activating photosensitizers such as your bilirubin, which can lead to ROS. By activation of bilirubin, it can lead to ROS formation by activating your ROS and RNase producing enzymes like your NOS or NOS, or by inhibiting antioxidant enzymes activity such as your CAT. There is a very important, all these examples need, I wanted to highlight it because there is a lot of evidence which indicates that there is an important role for ROS in carcinogens upon exposure to your genotoxins. So, probably suggesting the important role of your antioxidants or dietary natural products in the importance of their when you can't avoid your exposure to the genotoxins, maybe this antioxidants could play a role in providing having a favorable outcome or not progressive outcome for progression of the cancer. Now we have come to the end of this session and we have really seen what exactly, come back to my first slide where I was talking about the history. Earlier when those people when used to in UK especially, when they used to go to the coal mines, they used to carry caged canaries, that is with birds in them, that into the mine tunnels, that when there is during the excavation process, when there is built of this dangerous gas such as your carbon monoxide or anything collected in the mine, these gases would first initially kill the birds and then the miners would be affected. There is something obnoxious release, let's run away. That was a warning to exit the tunnels immediately. Now, do we have such kind of now we do not we can't afford for such kind of a mechanism, but still just relate my NGS slide, how we can identify the effect of a carcinogen on the DNA sequence. For example, I want to leave you with this story, like what if we have taken this bird DNA sequence and then go about it. I am sure lot-fold mechanistic studies could have been unfolded. With this we conclude this particular session, the molecular mechanisms of carcinogenesis, and we will meet up with a different session on precision oncology in our next class. Thank you.